Hello and welcome to this presentation entitled Extracting Individual Solar Cell Data from Photovoltaic Module Electroluminescence Images and Current Voltage Curves. My name is Alexia Suca de Acevedo, and I present this together with Kurt Tareto and Matias Cordoba. Electroluminescence imaging, combined with dark current voltage characterization, provides valuable insights into the structural and electrical properties of photovoltaic modules. In current research on electroluminescence imaging, a predominant focus lies on the methods meant for individual solar cells rather than entire modules, requiring the evaluation of isolated cell data. This study tackles this issue to attain a comprehensive diagnosis of modules at both the local and global levels. This is possible with a simple measurement setup based on the theory of electroluminescence. When a solar cell or module is supplied with a forward direct current, it will emit light according to the reciprocity theorem. Here, the electroluminescence photon flux emitted locally at a coordinate r on the surface of the module correlates to the voltage at that coordinate. Vt is its thermal voltage, and C is the calibration factor, particular to that coordinate, and related to optical and material properties of the module and the camera system. Imaging is achieved with a silicon-charged coupled device, sensor. The module is biased while placed in a dark environment. These measurements serve as the base requirements for the calculations to follow. In the measurement stage, module data is acquired in the form of electroluminescence images and the module dark current voltage curve. The diagram depicts this as the beginning of the process, in the top left corner. Inside the arrows, the information resulting from the calculations are displayed. These values feed calculations on the right side. The module global series resistance, calculated from the module dark current voltage curve, is utilized to assess the results from the methods proposed in this work. On the other hand, the electroluminescence images contain information on the local voltages in the module. The local voltage is a key parameter to evaluate local series resistance, and indirectly in this case, the global series resistance. To achieve this, each cell bias voltage is approximated by adding the highest voltage value within the cell to the voltage drop over an external series resistance. This voltage level will be used to generate the dark current voltage curve of the cell. This method requires two images, one at a lower current value to establish the calibration factor for the module, and another at a higher current value to set the current voltage relationship on the curve. This process can be repeated various times to obtain a comprehensive representation of the curve. The individual cell global series resistance can be calculated now from this generated curve. Ultimately, this data serves to assess the local parameters for each cell, as depicted on the right side. To achieve this, the voltage drop due to the series resistance is computed as the voltage drop between the cell terminals and the coordinate r. Current density is calculated using the single diode model. It is necessary to scale the final maps according to global cell series resistance values. In this work, electroluminescence imaging and dark current voltage characterization is conducted on a polycrystalline silicon module for in-depth study. The dark current voltage curve in the left side uses a module series resistance of 0.129 ohm. On the right side, an electroluminescence image of the module at 3 ampere injected current highlights cell number 16. Dark current voltage curve for this particular cell returns a series resistance value of 7.68 milliohm. The table on the right side shows the results for all cells. Dark saturation current density values could also be displayed in this fashion. The total module resistance calculated from the sum of these values is 0.128 ohm. Coming back to the original module dark current voltage curve, the series resistance values can be compared, showing excellent agreement. Generated maps provide quantitative data on local variations of these parameters for cell number 16. Displayed side by side, the maps distinguish contrasts due to variations in the dark saturation current density as well as series resistance. The combination of module electroluminescence imaging and current voltage characteristics delivers not only global module parameters but also individual cell properties, in this case current voltage curves and series resistance values. The information gathered also provides the necessary data for local characterizations of individual cells in terms of saturation current density and series resistance. This enables a thorough module diagnosis, both during manufacturing and after in-field use, or at the end of the module's lifespan. This concludes our presentation. Thank you for your time.